Welcome, dynamics students. This mini lecture is a problem demo that gives you some introduction to acceleration for a very simple case for rigid body planar motion. So in this case, we've got basically a cylinder or a disc, and it's being held down by a fixed point at its center. It's 0.5 meters in diameter, and it's got, and this is represented by the blue line, a cord that's wrapped around and around it like a winch or a yo-yo toy. And that cord is being pulled such that this any point on this cord here is accelerating at 10t, where t is in seconds, and then acceleration is 10t in meters per second. So this is a linear acceleration that would be applicable at a point tangent to the cylinder, right there. So this is a great place for us to deploy our general expression for acceleration of any point on a rigid body, presuming we know the acceleration on any other point. Someone wants to know what the angular acceleration, velocity, and displacement are at a given time. And that time is t equals 3 seconds. Somebody wants to know effectively alpha, which is angular acceleration. They want to know angular velocity, omega, and they want to know displacement, how many degrees or how many radians that cylinder has moved through by the time t equals 3 seconds, assuming we know what effectively the tangential acceleration is at any point, but it's kind of convenient that it's at a vertical point there where it's easy to slap a coordinate system down. So what is our general expression for acceleration on any 2 points on any rigid body that is undergoing planar motion? I won't derive these, but I will leverage them. We'll call this point out here point Q, and we'll call this point P there right at the center, the fixed pivot, P for fixed pivot. So acceleration of 1 point on a rigid body is equal to, and these are all vector quantities, acceleration of some other point on that same rigid body plus the angular acceleration of the whole rigid body, which is going to be by definition in the k-hat direction because we're only concerned with rigid body motion, crossed into a radius vector from point P to point Q. You can think of this as, say, we know the acceleration of point P, the radius vector from the known point, the point of known acceleration to the unknown, minus the angular velocity of the body squared times that same radius vector from P to Q. So alpha and omega concern themselves with the whole rigid body, and only that rigid body, but that's a whole body property, whereas radii and accelerations are concerned with points. So what we basically need to do is get some in. Here we have our expression, and this basically, in case you wonder, remember, because this is a vector expression, and it's going to have components in the I hat and j hat directions. If we use a coordinate system, that means we get basically 2 equations in one. But the problem is we have, without another piece of information, we have 1, 2, 3 unknowns. We can certainly get a radius vector if we use a coordinate system, but we got one extra unknown than we have an equation for. So we're going to have to think of something else we know about the problem. In the meantime, let's get a coordinate system going here. And I know this will produce a few signs that are a little bit wanky, but let's just use we'll use I hat, j hat, like this. This is kind of our standard notation. I hat, x increasing to the right, and j increasing upward, and that means theta is increasing in the counterclockwise direction, which is probably means we're going to, given just intuitively looking at this, we're probably going to get a lot of negative alphas, omegas, and thetas, but that's okay. We'll just use a negative sign. On this basis, our radius vector from P to Q, here's our PQ. We can define that as 0.5 meters j hat, and of course our acceleration is going to be in the I hat direction. So let's go ahead and rewrite our equation using what we do know. So we can say something about our acceleration of point Q is equal to 10t I hat. We'll just note that it's in meters per second. We would have to put units on our coefficient here to get it to all equal out when we start integrating and using seconds. So we're gonna very cautiously drop the units there. Not recommended as a general practice. Okay, so that's going to equal the acceleration of point P plus alpha k hat cross, and we've got 0.5 meters in the positive j hat direction minus omega squared, so that's the magnitude of the angular velocity, times 0.5 meters j hat, which is again our R P to Q. Okay, let's do a quick units check to make sure that we're going to get the right units. Even though we're not writing them, we know that our 10t should be in meters per second. We're going to do a TBD on our acceleration of point P, but we know alpha is going to be in radians per second square, multiplied by meters in our 0.5 meters, so we'll get meters per second squared. Our omega is in radians per second. We're going to square that, so we'll get radians squared per second squared. Radians are considered to be dimensionless, so we'll again get meters per second squared. So we've input our terms correctly. Next important observation we need to make is, if we look again, we'll get we can get two equations out of there. We can tally up everything in the I hat direction and everything in the j hat direction, but we still have alpha, omega, and a acceleration of point P, AP. Now we need another piece of information, and the piece of information that we're going to use is the fact that P is a fixed pivot. It has no velocity and has no acceleration. It's just sitting there. Q definitely has acceleration, and in fact it has acceleration both tangential and normal. But P is just sitting there. It's not accelerating. So we know this is 0. So we can rewrite our expressions and get something much simpler. So we can rewrite to our 10t as AQ, and we can work out our cross product here, and we can say alpha times 0.5 meters times k hat cross j hat minus omega squared times 0.5 meters j hat. So we can, let's get a direction on there. Okay, so this is now, we're down to two equations and two unknowns if we separate out our variables. So we can go ahead and work through our cross product. We know that k hat times j hat by the right hand rule is negative I hat. So we have 10t meters per second squared in the I hat direction. We'll just write meters per second squared over here. Is going to equal alpha times 0.5 meters times negative I hat minus omega squared times 0.5 meters j hat. Checking there. So let's collect some terms. We can say 10t, so we'll collect, basically we'll start with the I hat direction. So we can say 10t equals negative alpha times 0.5 meters, and then we can say 0 equals negative omega squared times 0.5 meters. So this is I hat terms, and this is j hat terms. Okay, have we got everything? I hats, I hats. Okay, well, what this says is that's 0. At least just looking at our acceleration expressions, there's no inherent angular acceleration necessary for q to have, angular velocity for q to have its acceleration. So the disk could be sitting, the cylinder could be sitting stationary, and we could apply a force and we have an acceleration, and we could get an alpha before the thing ever starts to move. That's not to say at 3 seconds it's not moving. So that means we may have to get our actual velocity as a function of time from some integration, and it may show up as a limit of integration. But just in terms of acceleration, given that configuration and the relative positions on the rigid body and what we know about the fixed pivot at P, this is 0. So we're left with basically, we can say alpha is going to be equal to negative 10t divided by 0.5 meters, and this was in meters per second squared. So that's equal to negative 20, effectively, 20t radians per second squared. Okay, so that's increasing with time. So there's our angular acceleration. If we wanted to know what it was at 3 seconds, we put in 3 seconds, and we'll just do a little tally up over here. We could say alpha at 3 seconds is going to equal negative 60 radians per second squared. Now it's negative, indicating it's going to be accelerating in this direction, which makes sense given the direction that we're pulling. So it's going to, the actual acceleration is clockwise. We've defined positive angular displacement acceleration velocity is counterclockwise, so we got a negative. So that's no big deal. Now we can integrate and get omega. And I'm just going to do a head integral. Actually, I'll just write it out. And we're going to start at time 0, and we're going to go to 3 seconds because we know that's the time of interest, and we're going to integrate our alpha, which is negative 20t per second squared with respect to time. And so we'll get negative 10 radians per second squared t squared from 0 to 3 seconds. 0 will give us 0, and so we'll end up with a negative 90 radians per second. Wait a minute. Oops. We should be getting this was a radians per second squared. I forgot. We're just going to have to ignore the units. This will end up being in 90 radians per second. haven't faithfully reproduced the units. That's why I like putting them on the coefficient. We know it's going to be in radians per second because it's an angular velocity, and again it's going the opposite way, so we have our omega at 3 seconds equals negative 90 per second. And then last but not least, we can integrate that again and get our displacement. So that's the integral from 0 to 3 seconds of omega dt, which is equal to the integral of negative t 10 t squared dt. I'm dropping the units now because we know this is just going to be in radians. So we get 10 thirds t to the third evaluated between 0 and 3 seconds. And that will again give us, and it's a negative, excuse me, so that'll again give us negative 90, except this time it's negative 90 radians. So basically we have 3 to the thirds, 27 divided by 3 is 9, so 9 times 10 is negative 90. So that's displacement. So you can think about this as if we do 90 divided by 2 pi, that's about 90 divided by 6. So you got maybe 15, basically it's going to go around about 15 times in 3 seconds. So our answers are negative 60 radians per second squared for alpha, negative 90 radians per second omega, and our total angular displacement is going to be negative 90 radians, which means all the negatives just mean everything is going in the clockwise direction. So important points. What did we need to know? First, we used our kind of universal expression for velocity of of acceleration of any 2 points that are on the same rigid body that is undergoing planar motion. So all in one plane, it can rotate, it can translate, it can't come out of the plane, it can't rotate out of the plane, it's rigid. So we can relate acceleration of any 2 points and relate those to the whole body's angular acceleration and angular velocity. Because we've got planar motion, we automatically have 2 equations in one. We're going to have our I hat and j hat expressions coming out of this. So we give ourselves 2 equations. We had 3 unknowns. We needed to know something else about the acceleration of one of these 2 points. We had q basically as a given, but in a way we needed to use that to solve for other things. So we needed to get p. Basically, we still had 3. If we didn't know q, we could say we had 4 unknowns. So we needed to know something about p, so we needed an additional piece of information in addition to the fact that p and q are on the same rigid body, and we know the acceleration of q. We had to know something about p. And lucky for us, it was simple. It was a fixed pivot, so we knew that was 0, and then the rest was just a little bit of vector algebra and a couple of integrations. This is another key finding over here. And what this kind of told us is we could relate back to Newton's second law and say, yeah, if I apply a force and get q to accelerate, that doesn't necessarily mean I have to have any angular velocity of that body at that instant. It means I'm going to get it because over time I'm going to integrate that angular acceleration. I'm going to get a velocity. But this was a nice little verification of our Newton's second law applied to a rigid body, that at that instant at t equals 0, you could say you don't necessarily have to have any velocity. So again, to get our velocity at time, just integrate, put in our limits, and then integrate again and get how many times we've gone around our radians, and we can divide by 2 pi and get revolutions. So that is the end of this simple demo. Obviously, we can expand on that two points on a rigid body relationship and relate multiple rigid bodies. We can have scenarios where we don't have a fixed pivot, where AQ and AP have both components acting, but it's all based on the same kind of principle where we're relating the accelerations of the 2 points. We may need to go back and use the velocity of the 2 points. There's an analogous expression for that we've shown in an earlier demo. And then use other things we know about the problem, about constrained motion. Is something moving along a line? Is something moving in a groove? To get additional information we might need. There's kind of a pattern to this that is all made possible by the fact we're in a rigid body and we're in planar motion. So that's it for this mini lecture, and stay tuned for more adventures in rigid body planar motion.